and many other higher form theories like standard model theories and weak interaction theory and strong interaction theory and many theories like gravity theories, not gravity theory actually, quantum gravity theories and string theory of course. So in this case we are going to discuss how the Abelian gauge theory is actually converted into the higher mathematical theory. This is called Young-Mills theory. So what happened exactly? So C.N. Young and James Mill, these are two guys who proposed this theory. So came up with a very beautiful idea of the gauge theory, in which the usual electrodynamic field had an internal vector space, which we call color space, attached to it, and which has the same structure as that of our ordinary vector space, that is three-dimensional space. The ordinary fields now have a dual structure. The fields have component in ordinary space as well as in the color space, so which do not affect each other. That means these two are independent of each other. So thus a scalar in ordinary space-time can be a vector in color space and vice versa. So a Young-Mills vector is expressed in a different manner. So this is actually in color space. So this is a sort of Lie space we call, where this Lie space is spanned by some generators or some basis vectors, which we shall discuss in a moment, right? So let us start with this. So Young-Mills theory. So this has a popular name as well. It is called non-Abelian theory. So let me first tell you what this Abelian means. So suppose we have two quantities. Let us say that A and B are the two quantities, and we are just writing a combination like this, AB and BA. So if we have two quantities and the order does not matter, then we call it Abelian. Where order does not matter is called Abelian. So why Abelian? Because Abel was the person, mathematician, who first introduced this concept. That is why in his name it is called Abelian. So in our usual notation we call it A commutator B equal to 0. This is called Abelian theory. Yeah, anything which is commutating is Abelian. And non-Abelian means where you have AB, this is not equal to BA. I'm not saying that this is equal to minus BA or something like that. It is generally not equal to BA. So ordering matters. Here ordering does not matter. And here ordering matters. Ordering matters. Right, this is what we have. So suppose we have a vector in space-time is denoted by the way like this, A mu. So this is a covariant vector, and this has 4 components. So mu equal to 0, 1, 2 and 3. That means we can have A mu equal to, in fact, A0, A1, A2 and A3. So these are the components for a space-time vector, and this is called your contravariant vector, and this has the components once again like this, A0 and A1, A2 and A3. And there is a convention. So convention is that, if you want to convert this mu into the covariant one contravariant vector, if you want to convert it into a covariant one, then you have to introduce a metric tensor, which we call here Minkowski metric tensor for the flat space-time. And so mu index here, and a new index I am writing here, new here, and then we have to write down this like this, a new. So see, new and new. So here it is in superscript, and here this is in subscript. So it is called contracted, and we here use the Einstein-Simpson convention. That means the contracted or dummy indices are summed over. That means if you like to write it, then mu has to be fixed here because it is 3 index. So 3 means single index, and double index means contracted index. So here we write A0, and then we can expand it like this: mu1 and A1, mu2 and A2, and mu eta mu3 and A3. Also the form of Minkowskian metric or flat metric eta mu nu. This is actually a matter of convention here. Most of the people actually adopt this convention. Eta mu nu equal to how much? We write it here like a matrix. Okay. So this is 1 0 0 0 4 cross 4 matrix minus 1 0 0 0 minus 1 0 0 0 0 minus 1, and in a nutshell we can write it here diagonal and 1 minus 1 minus 1 minus 1. So here you see the space indices. These are the space indices and the time indices. These are temporal indices. These two are very, very different. That means they have different nature. So if one is space is showing a negative signature, then time will be showing the positive signature. And we can have other convention as well. So other convention is that this is very popular convention nowadays. So this is minus 1 1 and 1 and 1. This is new convention, and this is old but popular convention. Yeah. So eta mu nu is known to you, right? So now a scalar in space time is given as, how shall we write it? A dot b. So this is a scalar. Okay, what we shall write here? A dot b means a mu and b mu, or we can write it like this: a mu and b mu. The condition is that mu must be contracted, and this can be written as mu nu also, and a mu and b nu, and also it can be written as eta mu nu and a mu b nu. So there are multiple ways to write the scalar quantity. So scalar quantity is the one which does not have any component except one. So this has a single component. So scalar quantity means single component object. So it can be something like this. It can be something the product of two vectors. Okay, and similarly a tensor is the one. A tensor in space time is the one which have, okay, what we shall have here, say we write T mu nu. So this is something a mu and inner product of direct product of other vector a nu, and similarly we can write T mu nu. This is how much? This is a mu and something a nu, and T mu nu is, this will be a mu and a nu. So this is the way we write a two-rank tensor. So here we have 1 and 2 indices, so it is called two-rank tensor. If it has 3 indices, then we can call it 3-rank tensor, and so on. This is the usual way of writing the things. Okay, so what about the Lie space? So in Lie space we call it Lie, not lie. Okay, हिंदी में लिख देता हूँ Lie. So in a Lie space, what we have? Lie space, what we have two vectors or three vectors. Let us say a vector is written as. How shall we write it? Let us say that this is a vector in Lie space. Okay, so this simply means this has some component. Let us say that a component and some basis component. This is an expansion of vector in the terms of the basis component, just like we have some vector in three-dimensional space, you remember. So we write it how much? We write it here ai and ei. So this is a1, e1, a2, e2 and a3 and e3, and e1, e2, e3, these are the basis vectors. So usually what we write here, a1 and a2 j and a3 k. Here e1, e2, e3 are basis vectors I, j, k. Similarly here a is some basis vector, we call it here a starting from 1, 2, 3. Okay, this has three values, this can have three values. So it is just simply looks like it just like our three-dimensional space, vector space as we know it. So in fact we shall write here lambda equal to lambda 1 t1, lambda 2 t2 and lambda 3 t3. This is what we have. Okay, so what is the connection between the basis vectors? So for three-dimensional space we know that, for 3D space we know that we have a connection between for the vectors, like I cross j, how much it is? K. Similarly j cross k, this is equal to I, and k cross I, this equal to j. And in a single format we can write here like this, a b c. Okay, or we can write here like this. So we can write in component form. So ea cross eb, this is how much? We shall write here epsilon a b c and ec, where abc here, abc are the indices and they run from 1 to 3. This is what we have, and these are your basis vectors. So in general we shall write basis vector as e, but in Lie space we are writing it by ta. Lie space we write it by ta. Okay, this is one way, and also we can write it like this, lambda a and ta. So in three-dimensional space we don't have any difference between the ta and ta. These two are same because we can have all the signatures same. But if it is in space-time, then we can have temporal component as well, which can have different structure or different signature than the in comparison with the spatial components, right? So there is actually so do we have anything like this for the TA vectors? Yes, we have. So the very first property for this is this TA and TB, their commutator is equal to I and FABC and TC. So what is this FABC? So this is called structure factor. We call it structure factor. Structure factor, and it is just higher analog of Levi-Sweeter tensor. Levi-Sweeter tensor. Let me correct it. This is what we have, right? This is higher analog of Levi-Sweeter tensor. Very good. So Levi-Sweeter tensor, you know, this is antisymmetric tensor, so it is also, hence if ABC is antisymmetric under exchange of indices. This means we if we write A, B, C and we just exchange A and B, so this is B, A, C, then it comes out to be minus of A, B, C and so on. Right? So this shows just cyclic behavior. And the other property for these tensors is this vectors TA vectors TA TB. We write here it, so not this one, sorry. So if you take the trace of this product TA and TB, trace of this product, so this comes out to be half of and delta AB. Delta AB is Kronecker delta. Is Kronecker delta. So which remains 1 if A and B are same, and becomes 0 if A and B are different. So a dot product of two vectors in Lie space. How shall we write it? We shall write it here like this, lambda A and something omega A, this is equal to lambda dot omega. So we have to specify which type of dot is this, because we have a dot for space time as well. So we have to be very precise which dot we are talking about. So this is your third property. And how the cross product is defined? So cross product is defined like this. So we write here, suppose there are two vectors lambda and omega. So the A component will be how much? Here it is F A B C and then lambda B and omega C. This is the way we define the cross product. And we can have a Jacobi identity as well. And this Jacobi identity, as we had discussed in the previous classes. So this is TA and TB and TC commutator. And then plus here we have, in place of A we shall write now B, and where we have TB we write here, in place of B we write C, in place of C we write A, and now in place A is there, B is there, and then we shall have a TC, and here we shall have, in place of TC we shall write TA, and in place of A we shall write TB, and this is equal to 0. So if we just break it, then structure factor wise Jacobi identity looks like this one, F B C M and F M N A, and then here we have C A M and then F M N B, and then we have F A D M and then F N M C. I'm sorry, MNC. It should be MNC. This equals to 0. Now here you see those quantities which are coming repeatedly, like this MM, and here we have MM. These are summed over quantities, right? These are summed over quantities, and okay, nothing else. So this is called Jacobi identity. This is very useful, and we shall show in a way that what it means exactly. So if you just like to write it down to prove it, then you can work it out. If you are really puzzled with that, then you can contact me. I shall explain it to you. This is what we have. Okay, so okay, and one more thing, that a space-time scalar can be a Lie vector. This is very important. So suppose, for example, we have this phi vector. Phi vector in space time, it is scalar because it has only one component. but in Lie space we can expand it as a vectors like phi a of x and then ta. Okay, so a vector in space time can be a scalar in Lie space. So like what? A mu, this is a vector in space time, but it is just a scalar in Lie space. There is no dot, there is nothing like that. Okay, this is what we are going to have. So we start with the Yang-Mills Lagrangian. The Yang-Mills, yeah, we can write here non-Abelian as well. Lagrangian density. So we start with very simple one. Likewise, the gauge theory we had in Abelian gauge theory we had the L for Maxwell. This is how much? This is -1/4 and F mu nu and F mu nu contracted, and we told that F mu nu is nothing but partial mu and A nu and minus partial nu and A mu. This is what we have. This is what we have. Right. So here what we are going to have here for the non-Abelian Yang-Mills Lagrangian, the corresponding Ym means Yang-Mills. So Yang-Mills Lagrangian density. So we know that a Lagrangian density always must be a scalar quantity. So not scalar quantity not only in space time but also in the Lie space. So here we shall write the analog of this. So F mu nu and dot F mu nu I shall write here. So here dot is the dot product in Yang-Mills space. So if you don't like it, then you can expand it like this: F mu nu and A and F mu nu and A. This is the way we write. And if you don't like it, then you can write -1/4 and delta AB and F mu nu A and F mu nu B. This is also a way to write the Yang-Mills Lagrangian density. And what this F mu nu is here? So this time it is a bit different. This time it is a bit different. We define the Yang-Mills field strength tensor like this: partial mu and A nu, and then partial nu and A mu, and then we write here I and the coupling factor. Let us say that GVF coupling factor. Last time we wrote Q, but so now on we shall write here G for the coupling factor, and then the A mu and A nu commutator. Okay, this is what we have. But remember, this is not in the ordinary space. This is actually, this is a quantity in Lie space. So we can write this quantity as F mu nu and A Ta, and then partial mu A nu A and Ta, and then partial nu A mu and A and Ta, and then we have the next term Ig and A mu A Ta. Now see, we have already used the A index, so we have to choose this time a different index. So here we shall write instead A nu and B and Tb. Now, so here you write the first term. So Ta is not these generators of Lie group, or the basis vectors of Lie group, are not function of space time, so we can pull them out. So this will act only on A, which is function of space time, and Ta will be free. Similarly, we shall have partial nu and A mu and A, and the Ta will be free. And here we shall have Ig and C. This time these are the space time indices. These are the space-time vectors. So we can pull them out because they don't have any problem here, because they are not going to commute anyway. These are just components like we had in earlier case. But TA and TB will remain there as a commutator. So we shall write partial mu and A nu, and here we have A and TA, and then minus of partial mu and A mu and A, and we have TA, and this quantity is how much? I G A mu A and A nu B. But this is what? F A B C and T A. So F A B C and T C. Okay, this is what we have. So F A mu nu and T A. Now here you see everywhere A is contracted, A, here also A contracted, here A also A contracted, here also A contracted. So in the first few terms we shall write, so we can replace all the contracted indices by some other index. We can replace, these are called dummy indices, okay? We can replace dummy indices by other indices, by some other indices. Why we are doing this? It will be clear in a moment. Indices. Let us show what it means. So we shall write, in place of A we are going to write here C mu nu and T C, or we can write partial mu and A nu and C and T C, and here also partial mu and A mu and C and T C. And this time we shall have this quantity is how much? This is the cross product. So here we shall write, what we shall write here? IG. What we shall write? IG cross. IG cross. So this is IG and a cross product of this. So here we write A mu cross A nu and C and T C. This is what we are going to have. One thing I forgot to mention. Somewhere I have just made a mistake somewhere. Yes, it is IFLC. So here we shall write I as well. Plus I. Yes, plus I. So we can write it here. So now here, see TC common, TC common, TC common, TC common. So we can throw it out. So we can write here F mu nu and C, and there we write partial mu and A nu and C, and partial nu A mu and C, and then I square means this is minus, so G and A mu cross A nu and some vector C. So C is a free index here. So you can replace all the C vectors by something else also. If you like it, you can write it A, no issues, because what you write on the left side, it must be right side as well. So this is very important. A, and A. Let us pack it because this is very important relation. Okay, so we got the connection for F mu nu A. So this F mu nu is a vector in, so this is F mu nu a vector in Lie space, as it has a index here, it has an index here, and a tensor in space time, because it has two indices here, mu and nu. So it has a dual character. Okay, so for one thing it is a vector, for one thing it is a tensor. and same happens with all the quantities which we see here. So now the Young-Mills Lagrangian density is what we shall write here, curly L and Ym. This is equal to minus 1/4 F mu nu and F mu nu, but we are going to write here a dot product. So this dot is for what? This dot is for uh, Lie vector. So remember, we can write this as well, F mu nu and F mu nu and A. Okay, so let us expand this and see what exactly we are going to get. So minus 1/4 factor is there. So F mu nu A. So we can expand from here. So this will be partial mu and A nu and A minus partial nu A mu and then minus G A mu cross A nu and A. This is what we have. Let me make it big bracket, and also we shall have here big bracket closed and partial mu A nu A and partial nu A mu A minus G A mu cross A nu uh, A nu and A. So we can expand it further, and let us do one thing. We can throw this minus 1/4 this side, so this will be minus 4 Lym, and this will be partial mu and A nu. Let me write it explicitly, then we shall work it out. A mu and A minus J A mu cross A nu of A, this whole thing multiplied with partial mu A nu A and minus partial nu A mu A minus G A mu cross A, sorry, not this way, uppercase A mu cross A nu and A. Okay, this is A here. Okay, so let us expand it. So first term will be partial mu A nu of A, and the other term will be partial mu A nu and A. Then we have partial mu A nu and A, and we have partial nu A mu and A, and then we shall have here the G factor is there. Okay, the G factor is there, so we shall write here, or we can do one thing. If we can expand it fully, or we can expand it in 4 terms. Okay, that would be fine. Okay, do one thing. We have not gone so far. So we have not gone very far, so we can make some amendment here. Okay, so here we write this quantity we take together, this quantity we take together. So we shall write partial mu A nu and A and partial nu A mu and A and partial mu A nu and A and minus partial nu A mu and A. And then we have minus G factor, and then partial mu A nu and A and partial nu A mu and A, and then here we have A mu cross A nu and A. The next quantity will be minus G A mu cross A nu A, and then we have partial mu A nu A and then partial nu A mu A, and then we have the last term as G square and A mu cross A nu A and A nu cross A mu of A. Okay, This is what we have. Why we have, no, a mu. A nu. Now it's fine. So here we see that we got, I mean, sort of expansion of two quantities. So the second quantity and third quantity, third quantity, this is just about twice of the factor. Okay, so we can write it like this. We can write it partial mu a nu a, partial nu a mu of a, and then we have partial mu a nu and then partial nu a mu, and we shall write a together, not individually. This makes the life a bit simple. And the third, and so this term and this term, these two terms just add up, and after summing them we get 2. Okay, 2 and g. So a mu cross a nu, and here we have a, and then partial mu a nu minus partial nu a mu, and overall a factor of a. And the last term is g square, and we have a mu cross a nu, and then dot a mu cross a nu. Or if you don't like the dot, then you can write here a and a. Now this is completely, completely summed over for a indices and mu indices both. Okay, so here you see the first term is how much? So this is actually multiplication of this and this and this and. Okay, so here we shall write something like this: partial mu a nu, and then partial mu a nu, and then we have partial mu a nu, and then partial nu and a mu, and then we have partial nu a mu, and then partial mu and a nu, and then finally partial nu a mu and partial nu a mu. So this is first term. Okay, and the second term is how much? 2g a mu cross a nu a, and partial mu a nu and a, and then we have 2g a mu cross a nu of a, and then partial nu and a mu a. Okay, this is plus, this is your plus, and the last term is g square a mu cross a nu, and then a and a mu cross a nu, and here we have a. This is what we are going to have. So here you see mu and mu contracted, nu and nu. So place is first place for the mu, second place for nu. Here we have nu and mu, just just like mu and nu, but in this case we have nu first and mu second. So these term and so these two terms are exactly equal. So we can write them as 2 partial mu and a nu, and partial mu and a nu. These two are exactly same, and similarly these two are exactly same. So partial mu a nu and partial nu and a mu. Okay, and these have an index oh, I have to write it as well. A and a. So a. Okay, and other term will be how much? This will be 2g. So nu mu. So what we can do here, we can just change the indices. So this will be actually 4g. So minus 2g here, and a mu cross a nu and a, and then partial mu and a nu a, and here we shall write, we just interchange the indices. So a nu and a mu, A, and then we have partial mu and A nu of A. What we did, we just changed the a mu by nu and nu by mu, and this will be same. So G square A mu cross A nu and A mu and cross A nu of A. So this will be 2 partial mu A nu A, and then partial mu and A nu A, and then here we have partial mu and A nu and A, partial nu and A mu and A. And the last term will be, okay, so here you see this is a cross product. So if we interchange the indices, so it will actually lead a negative answer. So it will be actually 4 G and A mu cross A nu and A, and partial mu and A nu of A, and the last term will be plus G square A mu cross A nu and A mu cross A nu and A. Okay, so now the deal is done. So here you see we have here 1 mu and 1 mu, 1 mu and mu. So it is actually quadratic in mu. So the field is quadratic, but here we have 2 field and 3 field. So this is actually cubic in mu field, and here we have 4, 1 2 3 4. So this is quadratic in mu vectors. So when we have okay, when we have any term having fields more than 2, we call that term interaction term. That an interaction term. So here we have for Young-Mill Lagrangian density, we have a 3 interaction term and a 4 interaction term. 4 interaction term. So let me write the 3 interaction term. This is what this is. Here we have this term is 3 interaction. This term is 4 interaction. So let me write it. So 3 interaction term means partial mu and A nu A, and partial nu and A mu A multiplied with partial mu A nu and A. So here we see A mu cross A. So this is your A mu cross A nu and A, and then partial mu and A nu and A. So it is very clear from here: 1 field, 2 field and 3 field, and all the 3 fields are same. That means all are A fields, A mu fields, A nu fields. That means they are all of same nature. So here we have 3 terms. So this is the interaction term, that is for sure, and and what? And we have here same field. So it is called self interaction. So when we have the same field, then we call self interaction. So self interacting 3. So A mu is called photon. Okay, so 3 photons. and there is a factor multiplied to this. This is how much? Here you see this is factor of G. Okay, so G is called coupling factor. A coupling strength of, so this actually this defines coupling strength factor. This is called coupling factor of 3 interaction. Similarly, we can have a 4 interaction. And 4 interaction is what? A mu cross A nu, and here we have A, and then A mu cross A nu and A. 1 term, 2 term, 3 term, and 4 term. So all the 4 terms are same. So it is called self-interacting 4 photons. And these photons are not simple. These are Yang-Mills photons. So a Yang-Mills theory in general, is a self-interacting theory. It has a deep meaning. What it means? Let me tell you what it means. So we know for photon we have no interaction term. That means the photons do not affect each other. They just behave as if there be no other photon. But the case is different. For Yang-Mills theory, photons. Yeah, we should call it bosons. In fact, bosons in general. So Yang-Mills boson, they show what? They show that they interact with each other. If there are 3, then they will interact. They are 4, then also they will interact. So in Feynman diagrams, in Feynman notations, we show it like this. So here it is called 3 interaction. Okay, so spring-like structures for 1 photon. So we call it A mu A, and this one is A nu A, and this is A something lambda. Or you can have the different indices as well, the Yang-Mills indices as well. So we can write it here, different quantities. So A nu B and A lambda C. Okay, this is called 3 interaction. Once again, I emphasize that this is your self interaction, and we can have 1 interaction like this. So here it is A mu and A, and A nu and B, and A nu and C. Sorry, not A nu, A lambda and C, and then something A sigma and D. So this is called 4 interaction. Okay, so I stop at this point and discuss the things in next lecture. So far, if you have any queries, questions, you are most welcome to ask the questions on your comment box. And also, I mean, if you have something to, I mean, add, then you can put your comment over there, and I shall, I mean, whenever I get time, I shall, I mean, go through that, and whatever the resolutions could be possible, I shall explain to you in the very next lecture. Thank you very much. And if you have not subscribed my channel, please subscribe it, and I mean, learn the things. I mean. I shall explain everything one by one, bit by bit. So need not to worry about anything else. This will be a complete package, and this will be very comprehensive. I mean, I shall try my best to make it very, very low and very comprehensive for even an average student. So thank you very much.